Google's central system for managing compute resources is called Borg. On Borg, millions of Linux containers process a wide variety of workloads. When a new application is spun up, Borg provides that application with the resources that it needs. Workloads at Google usually fall into one of two distinct categories: long-running application workloads, such as Gmail, and batch workloads, such as a MapReduce job. In the early days of Google, the long-lived workloads were scheduled onto a system called BabySitter, and the batch workloads were scheduled onto a system called Global Work Queue. You can imagine those names being quite apt because BabySitter, it's monitoring your long-running applications like a Gmail backend application, and Global Work Queue sounds like something where jobs are just processed and then taken off of the queue. Borg was the first cluster manager at Google designed to service both long-running and batch workloads from a single scheduler system. The second cluster manager at Google was Omega, and Omega was a project that was created to improve the engineering behind Borg, so Borg is still running. The innovations of Omega improved the efficiency and the architecture of Borg. More recently, Kubernetes was created as an open source implementation of the ideas pioneered in Borg and Omega. Google has also built a Kubernetes as a service offering that companies use to run their infrastructure in the same way that Google does. Brian Grant is an engineer at Google who has seen the iteration of all three cluster management systems that have come out of Google. As a principal software engineer with more than 10 years spent at Google, Brian has so much wisdom to offer around cluster management, scheduling, orchestration. He's the Kubernetes lead architect today, and it's really great to have had him on the show. He joins the show to discuss how the workloads at Google have changed over time and how his perspective on how to build and architect distributed systems has evolved. Full disclosure, Google is a sponsor of Software Engineering Daily. If you are looking for older episodes about Google infrastructure, we've told many of the stories of Google's early days and some of the more recent days as well. We have all of those episodes in the Software Engineering Daily apps for iOS or Android. We've got lots of episodes about blockchains and distributed systems and tons of other topics, and you can listen to all of those episodes in the apps. And you can also find them on softwaredaily.com, where we've got a community of software engineers that are posting projects and discussing the episodes. And if you want to become a paid subscriber to Software Engineering Daily, you can hear all of our episodes without ads. You can subscribe at softwaredaily.com. And also, all of the code for our apps is open source. So if you're looking for an open source community to be a part of, come check us out at github.com/softwareengineeringdaily. And with that, let's get to this awesome episode with Brian Grant. This episode of Software Engineering Daily is sponsored by Datadog. Datadog integrates seamlessly with more than 200 technologies, including Kubernetes and Docker, so you can monitor your entire container cluster in one place. Datadog's new live container view provides insights into your container's health, resource consumption, and deployment in real time. Filter to a specific Docker image or drill down by Kubernetes service to get fine-grained visibility into your container infrastructure. Start monitoring your container workload today with a 14-day free trial, and Datadog will send you a free t-shirt. Go to softwareengineeringdaily.com/Datadog to try it out. That's softwareengineeringdaily.com/Datadog to try it out and get a free t-shirt. Thank you, Datadog. I'm here with Brian Grant, Principal Software Engineer at Google. Brian, welcome to Software Engineering Daily.
Thank you. I'm happy to be here.
At Google, you've worked on 3 different resource management systems. You've worked on Borg and Omega and Kubernetes. How have the requirements of Google's cluster management evolved over time?
Yeah, so we described a little bit of this in, I think, a couple of the papers. Google started in the late 90s, which was actually just before the multi-core era. is when single core frequency increases was plateauing. And the early cluster management systems at Google focused on just finding a machine for an application. And there were two systems. One was BabySitter, and that was for continuously running services. And the other was a global work queue, which was for batch applications. So as Google started to evolve and get more diverse types of workloads that it needed to run, and as the platforms and our data centers started to increase in number of cores, it became clear that the existing find a machine approach wasn't going to be sufficient. So Borg was really born out of that when new applications were being created and when more resources were available on each machine to try to create a system that could pack multiple applications into each machine. Since then, that was around 2003, 2004. Since then, Borg has continued to be developed and evolve continuously. Since then, the later efforts came out of more specific needs, which I guess we're going to talk about later.
Yeah, I interviewed Louis Ryan about API infrastructure a while ago. He is now working on Istio at Google, and he talked about a few of the major milestones in how the API traffic changed over time. Namely, there was the growth of mobile traffic, there was the growth of the public cloud. Did these kinds of upticks in traffic, did they also affect how cluster management needed to proceed?
So I think mobile and Internet of Things affected certain aspects, such as networking. For example, IPv6 is a necessity for communicating with vast numbers of client devices. For the cluster management itself, I think it was much more driven just by Google's scale more than anything else. So we had a need for larger and larger data centers and larger clusters to run more and more applications as the set of things Google was doing was expanding over time. So throughout, I think, the whole first decade of Borg's existence, for example, just that scaling was a constant pressure, exponential scaling. As the number of workloads really started to explode more in more recent years, there became more demand for automating the management of the applications themselves as opposed to just managing the resources. So I think that's a big shift that's happened somewhat concurrently with the development of public cloud, but I don't think it's a direct consequence of it.
So it sounds like there's not any particular key event that sticks out in Google's timeline as having changed the requirements for that core infrastructure. It's more a steady exponential uptick in the demands.
I think so, yes.
Why have you focused on cluster management? Why not something else like machine learning systems or databases? Why has cluster management been your curiosity?
Prior to cluster management, I worked on high performance computing and actually compilers, dynamic compilation in particular. There were a couple of interesting ties with cluster management. One is, well, first of all, it was just a super important problem to Google. All of Google's businesses depended on this infrastructure working really, really well. And then the connection with my prior background was that it was a very infrastructure-centric kind of project, and that's the type of project that I've always gravitated towards. Actually, growing up, I was lucky enough to build a computer as a child, and from that point, I was fascinated by understanding how they actually worked and how programs actually ran on them. So I've gravitated towards lower-level systems like compilers and operating systems and high-performance computing.
These systems like machine learning systems or databases, high-performance, high-volume databases, these are systems that ultimately run on top of the type of cluster management systems that you have been working on for the last decade or so. Do you have any interesting stories of deploying these kinds of systems on top of a cluster manager where, because machine learning systems and databases, I think of these as applications that they could put unique pressures on a cluster management system. Have you ever seen one of these things deployed and have it expose a problem with the cluster manager that you didn't previously see with just generic services running on top of the cluster manager?
Oh, yeah, definitely. There are actually a number of kinds of applications that have had unique demands. Machine learning, one of the first things that we stumbled on was actually how to expose the various kinds of hardware accelerators like GPUs in the environment, especially in the early stages. One of the things I did prior to Google was actually GPU work, high performance computing on GPUs. In the very early stages, they were not shareable, for example, which is kind of contrary to one of the driving motivations behind Borg, is to be able to share resources on a machine. Also, Borg treats tasks mostly independently, but multi-machine machine learning workloads needed to pay attention to the network topology between the instances in order to get optimal performance, because the whole value proposition of doing these workloads on GPUs, for example, is to deliver extremely high performance, but there were a lot of tricky performance, very steep performance cliffs that needed to be avoided. So those definitely placed new demands. Storage systems, actually all of our storage systems in Google run on Borg. So especially the ones that are very, very widely distributed have a number of special requirements that Borg wasn't really designed to run those types of workloads. So things where the life cycle management of the underlying infrastructure, for example, storage devices, becomes intertwined with application level concerns and vice versa, were a bit tricky to model inside of Borg. So I'd say there have been several of these. Just another simple example there, they all have this flavor of requiring some kind of special access to devices that was not really anticipated, like tape backups. Tape drives only are on particular systems, for example. So yeah, there are been a bunch of different examples of that over the years.
Do you find yourself having to talk to hardware teams or data center teams in order to figure out how to implement this stuff correctly, or does your
absolutely. There have been some proposals for new hardware systems that have been changed because they would be too hard to fit into the Borg model. So we actually engage with our platform teams that are developing new systems at very early stages to make sure that there aren't mismatches, like things that would be almost impossible to implement in Borg, for example.
Software workflows are different at every company. Product development, design, and engineering teams each see things differently. These different teams need to collaborate with each other, but they also need to be able to be creative and productive on their own terms. Airtable allows software teams to design their own unique workflows. Airtable enables the creativity and engineering at companies like Tesla, Slack, Airbnb, and Medium. Airtable is hiring creative engineers who believe in the importance of open-ended platforms that empower human creativity. The mission of Airtable is to give everyone the power to create their own software workflows. From magazine editors building out their own content planning systems, to product managers building feature roadmaps, to managers managing livestock and inventory. Teams at companies like Condé Nast, Airbnb, and WeWork can build their own custom database applications with the ease of using a spreadsheet. If you haven't used Airtable before, try it out. If you have used it, you will understand why it is so popular. I'm sure you have a workflow that would be easier to manage if it were on Airtable. It's easy to get started with Airtable, but as you get more experience with it, you will see how flexible and powerful it is. Check out jobs at Airtable by going to airtable.com/sedaily. Airtable is a uniquely challenging product to build, and they are looking for creative front-end and back-end engineers to design systems on first principles, like a real-time sync layer, collaborative undo model, formulas engine, visual revision history, and more. On the outside, you'll build user interfaces that are elegant and highly customizable, that encourage exploration, and that earn the trust of users through intuitive, thoughtful interactions. Learn more about Airtable opportunities at airtable.com/sedaily. Thanks to Airtable for being a new sponsor of Software Engineering Daily and for building an innovative new product that enables all kinds of industries to be more creative. So, as you have alluded to, the first unified container management system at Google was Borg. What was going on at Google around the time Borg was created? Can you set some more context for just what was happening when the first widespread cluster management system was defined and implemented?
Yeah, I touched on that a little bit earlier on the hardware side. It was the start of exponential number of growth in the number of cores per box. So that was one thing that was happening. And on the Google side, it was MapReduce was being developed around that same time. And it was clear that the existing global work queue based solution was not going to be adequate, especially for the newer hardware. Our web search platform was being redesigned, again, to take more optimal advantage of the newer hardware. So there are these big new systems, applications really, that were being developed around the same time as Borg was developed. And it has actually made a goal to ship Borg able to run these key new applications.
If I recall the paper correctly, and you touched on this earlier also, but the BabySitter and the global work queue, these were the early systems that were for processing. BabySitter was if you've got some service that you want to deploy and it's a long running job. It's like you want your Gmail service to be up. It's not a periodic bursty workload. It just sits there and serves traffic. Whereas if you have something like a nightly MapReduce job, this would be something that would go in the global work queue. Is that the right definition for those different schedulers that you had pre-Borg?
Yes, that's right.
And so Borg was the answer to the question, what happens if we just combine all of our scheduling requirements into one system that can handle all of those things, right?
Yes, although I don't know that was originally the main goal. But, we wanted to improve utilization of these newer systems that had more resources available. We knew we'd have to carve up the resources and divide them between different applications. So I guess it became clear that there were two reasons why we'd want to address both categories of workloads with the same system. One was it was going to be hard enough to build one such system, much less two such systems. So just amortizing the work and complexity and the number of different systems users inside of Google would have to deal with and things like that. And the other was we actually use batch jobs to fill unused or underutilized resources that are reserved by services. So because there are different or more relaxed requirements with respect to things like latency and availability of the batch tasks, for example, they can be killed and restarted with less user-facing impact or no user-facing impact. We actually run those workloads at lower priority than the user-facing production service workloads. And we're able to push utilization higher by filling the gaps effectively with those workloads.
Borg was created at a time when Google had invested significantly in hardware that did not support virtualization. I think this was in one of the papers.
I think no hardware supported virtualization when Google started.
Right. Okay. Fair enough. But of course, in today's Google infrastructure, the containers, do the containers in Borg run on VMs or directly on host machine? Or maybe you could talk a little bit about Google's evolution towards virtualization, purchases of virtualization supporting hardware and deprecating that old hardware, what that trial and tribulation looked like.
Well, in general, Google updates its hardware as it needs to in order to provide significant new value or lower cost or new capabilities or things like that. So virtualization, I think, mostly did not come into the equation when we replaced all the non-virtualization friendly hardware, actually. The development of key kernel features that support containers like cgroups were actually motivated by Borg and the need for stronger resource and performance isolation of the workloads we had running on bare metal effectively in Borg. And I think, virtualization doesn't actually fully solve that problem. If you need to partition the use of CPUs or memory, especially at a fractional CPU level, virtualization alone doesn't get there. So we actually invested a lot in the kernel mechanisms, including those that are underpinnings of all kinds of containers today for Linux, so that we could pack applications more densely in Borg. We do have VMs running on Borg, like Google Compute Engine runs on Borg. So those are VMs on Borg, but Borg jobs do not run in VMs.
Okay. I guess I learned something new today. So there is just, you really don't even need to have VMs running within your organization, if containers do the job, unless you have a cloud service that serves customers that require VMs.
Right. And there are some special concerns like security concerns about untrusted applications, and cloud customer applications would be one example of that. But we developed a variety of sandboxing technology over the years to address those.
Yeah. I think about that even on the client-facing side. If you think about a Chromebook, I just think of this very lightweight sandboxed client-side browser tab that's probably interfacing with a server-side container, and I don't see where a VM would need to fit into that equation. So Borg evolved with Omega. Omega is described as an offspring of Borg, and there's several papers about Omega. What were the key evolutionary developments that occurred around the time of Omega?
Yeah, so Omega came at a time where we were facing challenges with the evolution of Borg. There were a number of new use cases that were hard to support and cluster management scenarios that were becoming fairly complex. And like we described, the interaction of all the different systems involved as, spaghetti or Rube Goldberg machines or things like that. So we're looking at trying to come up with a cleaner design that was more extensible, that could accommodate the steadily increasing number of scenarios and systems that needed to be supported. So it was really targeting the Borg control plane, the very lowest levels of the Borg control plane, not so much the user-facing pieces, but looking at questions like how can we support multiple kinds of schedulers for different sorts of different demands being placed on resources. And that's what the Eurosys 2013 paper mostly focused on, is the multi-scheduler architecture. But really, we were looking for how to come up with a cleaner, more extensible, less monolithic design that would make it easier for us to add more functionality over time.
When you have such a wide variety of users that are going to schedule jobs onto Borg or onto Omega, whatever your cluster scheduler is, what are the different axes of scheduling priority that you want to enable them to specify? Because that sounds like what you're suggesting here is at least one side of the evolution towards Omega is you've got all these different types of jobs, and how can we give all of our developers the right tunable priority for how they want to schedule jobs? Am I hearing you correctly?
Yeah, it wasn't even just a matter of priority. It's more a matter of criteria, right? So with Borg actually has a priority and preemption scheme built in that has arbitrarily fine granularity. So you could make decisions in a pretty straightforward way about which individual task should displace some other individual task. But if you needed to change what criteria were used to make a placement decision, or change how the resource reservation was modeled, or change how underlying hardware resources were accessed, or change how Borg's application level scheduler interacted with other maintenance activities at the system level or at the hardware level, for example, where you might need to model the actual underlying resources in a different way. Those use cases are where it was becoming tricky.
So the other thing you mentioned was that there was some spaghetti code associated with people who had to interface with Borg sometimes. So I don't know the history of the setting up the configuration of your cluster, but I know that with Kubernetes, it's a declarative syntax where you just define in declarative syntax what you want your cluster to look like at any given time. And if something gets perturbed, then the cluster will self-heal. And I can imagine different imperative language definitions that would probably be more prone to developing spaghetti code. Is that what happened? Was it imperative? Were the previous language definitions for creating your cluster, were they imperative rather than declarative?
Yeah, so just to clarify, this spaghetti came from systems that were trying to do things that weren't directly modeled by the Borg API at all. So there were kludges in place to try to interoperate in a reasonable way with Borg. So that's where a lot of the spaghetti came from. As far as the Borg's API, it's described a little bit in the Borg paper in Eurosys 2015, but the primary abstraction was job. And job was a parallel array of tasks where each task executed as an individual container that was scheduled onto some machine. And that model is kind of a not fully declarative. It did have a mostly create, read, update, delete kind of imperative API, but it was fairly restrictive. It was somewhat high level. There was just one API for all types of workloads. And because the tasks, there was no task API really, things like update strategies and the like had to be baked in to the business logic of that API. And that's, again, something that kind of drove a lot of complexity as the API needed to be expanded to run all different kinds of workloads.
A component of any distributed systems architecture, well, at least most distributed systems architectures, maybe not like blockchains, I guess, but there's often this centralized transaction-oriented store. Like with Kubernetes, you have etcd. With previous systems, you had Paxos-based stores. I think etcd is Raft-based. But maybe you could describe the evolution of the transaction-oriented store, if there were any mistakes that were made in Borg, or how it evolved towards Omega and eventually Kubernetes.
Yeah, I think the main Borg started with its own transaction log that was not even run as a separate service. It was just embedded into the control plane. And I think from my perspective, the disadvantages of that were in terms of scenarios like disaster recovery and such, the getting direct access to the storage system without the control plane in a healthy state was basically impossible. So splitting that out into a separate service that's actually just focused on maintaining that state decoupled from the business logic, in my opinion, makes it easier to operate. And having it be centralized instead of decentralized, I think also tends to make it easier to operate. Like some people have suggested, well, what about peer-to-peer or other approaches? But then you have to question about, well, how do you do things like backups of the state? Or, and it also just expands the operational surface area for the number of instances you need to manage and things like that. So if you can scale with a smaller number of instances, that tends to be simpler operationally. Whether it's Raft or Paxos or whatnot, doesn't so much matter. I mean, most of those all work similarly enough, at least with additional optimizations on top of them, some kind of leader elected transaction store. Omega's model was a little bit different than at least etcd v2 in that it did allow multi-record transactions, atomic transactions across multiple records. And that was mostly used to be able to factor resources into more granular records in the transaction store, as opposed to being used to mutate lots of unrelated things together in the same transaction. I think one thing we changed in Kubernetes compared to Omega was that we didn't allow direct access to the store to all of the control plane components. Basically, the only component that interacts with it is our API server. And that allows us to impose higher level semantics on top of the raw store, like authorization policy, validation, translation from one representation to another, things like that. And that is a better model we have found for supporting a larger, more diverse set of control plane components, including components that users may build and want to run on their cluster. Providing direct access to the storage system could be a very dangerous thing to do without adequate mechanisms for ensuring that they're not corrupting the state, for example.
The third container management system developed at Google after Borg and Omega was Kubernetes. And I've done some interviews with the other early contributors to Kubernetes, Brendan Burns, Craig McCluckey, and Joe Beda. When did you get involved with Kubernetes?
Yeah, so I was involved with Kubernetes from very early on. We actually, back in 2012, there was a mandate to have our internal infrastructure teams start to work together more closely with our cloud teams. And that work started then. And that was around the same time also that for Borg and Omega, some of these concepts like pods and labels, watch API, things like that were actually being developed for our internal systems. And then the next year, 2013, is when Docker was starting to become better known. And that's when Craig, Brendan, and Joe really started to come up with an idea to build a project around Docker. So it came out of that marriage of taking the expertise from our internal infrastructure systems, and we have several engineers who worked on various parts of Borg, working on Kubernetes today here at Google still, and working with our cloud teams to kind of elevate the abstraction above VMs to that container application and service level abstraction, where we can provide portability, more automation, and more of the kinds of capabilities that we have internally.
And as Kubernetes was getting off the ground, you saw the other container orchestrators cropping up outside of Google, the open source ones like Docker Swarm and Mesos. Did the external evolution of those different container orchestration frameworks, did those serve as any inspiration for what you were building internally with Kubernetes?
In a way. So 2013, when the actual coding on the project started, there weren't a lot of other systems of that nature. There was no Docker Swarm. And in fact, even what was announced at the same DockerCon in 2014 when we launched Kubernetes, that was LibSwarm, which was basically a simple library client that could start and kill containers on multiple hosts if you told it which containers you wanted to run on multiple hosts. It was a fairly simple thing, but that's one thing we saw a lot of people doing is these very simple orchestrators that would effectively be automating scripts that you would write by hand to do this on a handful of machines in a very sort of imperative and brittle way. So we saw a big window of opportunity where we had a very clear idea of what was possible and where we saw the space going. We did consider Mesos, and some of the folks who worked on Mesos interned at Google, and that's where one of the Omega papers came from, for example. But they weren't yet targeting Docker, and we felt like some of the design choices that had been made weren't a perfect fit for what we wanted to do, especially for running in a public cloud environment where we felt the additional resource management layer wasn't strictly necessary. So we decided to start from scratch, which had also the benefit of being simpler and enabling us to choose Go as the language, for example, which others in the space like Docker and etcd had chosen. So there was some evidence that developers in the space seemed to like it. So it gave us a clean slate where we could try out a bunch of these ideas that we had been developing internally over the previous few years.
The octopus, a sea creature known for its intelligence and flexibility. Octopus Deploy, a friendly deployment automation tool for deploying applications like .NET apps, Java apps, and more. Ask any developer and they'll tell you that it's never fun pushing code at 5 p.m. on a Friday and then crossing your fingers hoping for the best. We've all been there. We've all done that. And that's where Octopus Deploy comes into the picture. Octopus Deploy is a friendly deployment automation tool, taking over where your build or CI server ends. Use Octopus to promote releases on-prem or to the cloud. Octopus integrates with your existing build pipeline, TFS and VSTS, Bamboo, TeamCity, and Jenkins. It integrates with AWS, Azure, and on-prem environments. You can reliably and repeatedly deploy your .NET and Java apps and more. If you can package it, Octopus can deploy it. It's quick and easy to install, and you can just go to octopus.com to trial Octopus free for 45 days. That's octopus.com, octopus.com. Since then, Kubernetes has been widely adopted, and the adoption of it has brought a lot of changes to how people are thinking about the architecture of their backend infrastructure, as well as the discussions around cloud providers and how you should think about your cloud provider strategy. And when I started covering this space, I got the impression that, okay, it's great to have a container orchestrator because it puts a partition around your infrastructure where you could lift and shift it from one cloud provider to another and you wouldn't be locked in. And that's true. People can do that. But what I have seen more of in practice in talking to people is that they want to use Kubernetes as a vessel for multi-cloud. And so it's a way of, if you're on one cloud provider and you want to have access to the APIs or the lower cost of infrastructure on another cloud, you can set up a Kubernetes cluster, and it gives you kind of a home base to define your APIs and interact with other pieces of infrastructure. And now I know you've been at Google for a while, and you probably haven't really seen Google doesn't need to be multi-cloud because it is a cloud. But I'm sure you've talked to a lot of people. Are you seeing more of the lifting and shifting, or are you seeing more of the multi-cloud? And when you're talking to people, how are you seeing their cloud strategies evolve?
Yeah, one thing I'm definitely seeing is people want to take advantage of the capabilities that Kubernetes have for managing their workloads. So they want to run all of their workloads on it, databases, data processing, machine learning, CI, whatever it may be, to take advantage of those capabilities. And even simple things like a consistent way of specifying their command line, or a consistent way of probing whether their applications are still behaving correctly, doing health checks, those kinds of things. Getting that consistent operational experience where they can effectively do an API query to see what's running and what state it's in. Users have really embraced that. And having that consistent environment be everywhere they want to run is something they naturally then also want. And that's definitely one of our goals with Kubernetes, was to make it portable and make it ubiquitous. And I'm happy to see that it is now. I think that's great for users, and it does really enable multi-cloud in a way that wasn't really possible before, because not that you necessarily want to run the same workload across multiple clouds, but you can run workloads in the same way, using the same tools, using concepts that you're familiar with, using the same workflows anywhere that you want to run, whether it's on Google's cloud or another public cloud or on-premise. And it might be a private cloud, or it might even be bare metal. It might even be your laptop. And recently, a user told me a story where one of the capabilities that Kubernetes really unlocked for them was on-demand provisioning of integration test environments, for example, that previously they had to be set up by hand, potentially had to get repaired by hand, and then people had to schedule time to run their tests. And with Kubernetes, they can just use a tool to spin up all the application and all of the components it depends on, run their tests, and then tear it all down, all automatically. So it's those kinds of scenarios, I think, that really resonate to me. So yeah, I do see people using it multi-cloud, but I think the generalization of that is people just want that consistent foundation everywhere.
Yeah, or you see a lot of companies where they have a single QA environment where it's like, if you want to do your QA testing, you got to wait in line to deploy your new version of the software to that QA environment, and then run your tests there, and then somebody else gets to run their tests there, as opposed to if you have your environments are so easy to set up and destroy because they're defined as just easy Kubernetes commands, then it lowers the barrier to people testing individually in parallel and so on.
Absolutely. And you could potentially do something like that with Terraform and virtual machines. But a problem you quickly get into is that Terraform doesn't really attempt to abstract away the differences between the different cloud providers. And virtual machine images are not nearly as portable as container images. So really, it would have to be handcrafted for each environment you want to run in. And then if your test environment is different in any way than your production environment, then the benefits that the coverage you're actually getting from that testing is not nearly as good as if the environments actually had matched with higher fidelity.
Do you think Kubernetes is going to be the last container management system that you'll have to build, or do you think there's going to be another one?
I think it would be a bold statement to say it will be the last one. And in general, what we see is that these things get rebuilt every decade or two as there are new ideas, as requirements change. So I'm hoping that Kubernetes will have a lifespan of at least 20 years, and I think that's easily possible. Linux, I guess, is what, almost 30 years old. So something in that realm would be good. But yeah, I think to say, to generalize that even a little bit, the more general space, I think, is just automation of applications, of operations, of infrastructure. I think we'll continue to see innovation in that space of various kinds. And we're seeing that with service mesh and Istio, for example, where now there's a whole new category of infrastructure and application level concepts being orchestrated. We're seeing it with functions. So, as people try to automate everything in order to be able to make lives easier for users, but also scale to much higher levels. Like we're seeing, we mentioned this explosion in mobile and IoT on the number of clients before. Now we're seeing this explosion in the management space, in data centers and in public clouds. And people are going to need more and more tools and more automation in order to automate that without hiring more and more people to manage it. So we actually have a policy about that inside of Google, or at least aspirations or a goal. I think we probably talked about it in the SRE book, where we try to ensure that our operations staff scales sublinearly with the scale of the applications being managed, right? Because if the applications are growing exponentially, you don't want to have to hire an exponentially growing set of people to manage them. So part of the job description for managing applications at Google is also building additional automation so that we don't need to hire more and more people at an exponential rate.
Has anybody charted that out to see if it's actually sublinear?
Almost certainly.
Okay. I hope the results were good. Otherwise, perhaps it doesn't bode well for those operating large-scale infrastructure.
Well, we see that users want to offload more and more services onto cloud providers and other SaaS providers, for example, right? They want their services managed so they don't have to manage it. So it's the same goal, but they're just shifting the problem to the people who are running those services. And yes, those people running those services will not be successful if they're doing just as much work as the union of all their customers would have done.
You mentioned Linux's dominance for the last 30 years, or it's risen to be so dominant. Are there ever things in the host OS, in that Linux, or the host OS, the Linux substrate, that you question, where you think, I wish we just had a better operating system, or is there something at the lower level that you ever think could be changed that would be better for what has been built on top of it?
Oh, absolutely. I think there are a couple of different answers to that. And one is that Google has been contributing to Linux for quite a long time to build some of those things that are actually needed. I mentioned C groups, for example, and not all operating system concepts and resources are containerized. Some things are still managed per process. So if we can get more of those sorts of things isolated into container level primitives, either C groups or namespaces, I think that will just improve the kinds of management that we can do on top. And that's an ongoing process. Even user namespaces haven't completely matured yet and rolled out everywhere. So I think that will be an ongoing process. We still have some things that we proposed to the kernel way back before Docker several years ago that didn't get merged. Some of those things we may go back and try again now that a lot more people are using containers than just Google. On the other side, we're seeing a lot more container optimized operating systems. So in operating systems like Red Hat Enterprise Linux or Ubuntu, users are trained to install a lot of packages directly into the host operating system to run the kinds of applications that they want to run on those systems. And we're seeing movement away from that to much more stripped down distributions, lighter weight. And in many cases, they don't even have a package manager associated with them. They just have images with base services that can run containers, and then applications are expected to bring all of their own dependencies with them. So I think that general trend will continue, and I think it's a good one. Honestly, I wish I had containers on my Mac. It makes things so much easier. So I think we'll see that model really start to take off. The surface area of what you need to vet in your compliance and security audits, for example, just becomes so much less on the host OS if you just strip away all the things that are only needed by applications or only needed for certain administrative actions, things of that nature. You can isolate all of those things and then really start to understand what things are needed and why and where.
And when you start to talk about running your client operating system, like your MacBook or your phone, in terms of containers, is that to say that you would want to have something like a Kubernetes on your client device?
Well, I don't know that I would need something like Kubernetes per se to run my laptop. It might be fun, but it's more since I started using computers, I don't know, I was 9 years old. One problem has been installing multiple pieces of software on the same system has always created some problems or some challenges, whether it's DLL conflicts in Windows or what have you. And I think containers provide both the application file dependency isolation that is super beneficial to just cleanly keep each application completely independent from the other, so you can easily install them and uninstall them and upgrade them all independently. But also the resource isolation so that you can manage more cleanly how much resources to devote to different applications. Like I would love to be able to just take away resources from my browser in order to do some development, for example. Another thing that I think that containers can do really well is package up all the dependencies needed for a development environment, right? So one pain point for me, if I download code and install it and try to develop it, is that I may not have all the tools necessary to build it on my local machine, for example. If I can just package all those into a container image, then my job is simpler. I don't need to figure out what version of the compiler do I need, which build system do I need, and what version of it do I need, and what environment does it expect, and how should paths be set up, and all that crazy stuff that every developer has to go through.
I know we're at the end of our time, but just to close off, you've been building these kinds of systems for more than a decade. Do you have any parting thoughts for people in the audience who are building some kind of distributed system, something that involves a scheduler or large volumes of infrastructure? I know there's a lot of people out there building blockchain-related applications based on the listener responses from the most recent episodes, but it can or cannot encompass the design of blockchain applications. Just any words of wisdom?
Yeah, actually, one thing that came up in a conversation I had earlier today with someone, understand what use case you're optimizing for. Many of these systems have many engineering trade-offs that need to be made. Presumably, the reason you're building a new system is that the existing ones didn't address some use case as well as you would like. So be really clear about what use cases you're optimizing for, because you're not going to be able to address all use cases equally well. I think the other thing I feel like sometimes it's my job just to chant is pay attention to separation of concerns. Like one system, one tool doesn't necessarily have to do everything. Sometimes it's better to draw the bounds of scope of your system and define the integration points with other systems so that you don't have to make a set of trade-offs like across a much broader space than you intended. And you can allow people to make different trade-offs in the systems that they would integrate with yours. I think those are the two main things I would say.
Brian Grant, thanks for coming on Software Engineering Daily.
Thanks. Been great. I really enjoyed it.
Users have come to expect real time. They crave alerts that their payment is received. They crave little cars zooming around on the map. They crave locking their doors at home when they're not at home. There's no need to reinvent the wheel when it comes to making your app real time. PubNub makes it simple, enabling you to build immersive and interactive experiences on the web, on mobile phones, embedded into hardware, and any other device connected to the internet. With powerful APIs and a robust global infrastructure, you can stream geolocation data, you can send chat messages, you can turn on sprinklers, or you can rock your baby's crib when they start crying. PubNub literally powers IoT cribs. 70 SDKs for web, mobile, IoT, and more means that you can start streaming data in real time without a ton of compatibility headaches. And no need to build your own SDKs from scratch. And lastly, PubNub includes a ton of other real-time features beyond real-time messaging, like presence for online or offline detection, and access manager to thwart trolls and hackers. Go to pubnub.com/sedaily to get started. They offer a generous sandbox tier that's free forever until your app takes off, that is. pubnub.com/sedaily, that's pubnub.com/sedaily. Thank you, PubNub, for being a sponsor of Software Engineering Daily.
Wow.